before we talk about the second kind of conservation, which is momentum conservation, let me first offer you some knowledge on stresses. We know that at one point in the fluid, it has a stress state, right? So the stress state can be represented by this thing, which is called the stress tensor. The point in a fluid, if we enlarge it, what will it become? It's just a fluid particle, right? A fluid particle. So actually, the stress tensor represents the surface stresses acting on our fluid particle. Usually we can write the stress tensor as something like this: P11, P22, minus P33. Well, there are maybe other books and there are books and people that use different notations than me, but this is the notation I choose to use because I think it makes sense and I'm most used to that. Okay, so I'll stick to this kind of notation. So we see two things. First, some of the stresses are denoted by tau, but others are denoted by P, right? So what stresses I call them to be tau and what stresses I call them to be P, I'll tell you immediately. But now let's address to another issue, which is the indices. What do the indices mean? We see every stress have two indices, has two indices, right? So the first index represents the surface on which the stress is acting, and the second index represents the direction in which the stress is acting. What do I mean by that? I'll give you an example. Let's establish the coordinate system. So can you tell me, what will this stress be called? This stress is acting on the upper surface of the cube, right? So first we need to find on which surface the stress is acting. It's on the upper surface, right? So how can we represent a surface by just one index? By its normal, right? I think you are familiar with this notion. So we see that the upper surface is perpendicular to the x3 axis, which means we can call the upper surface. Well, of course, if the stress is acting on the lower surface, we will also call it to be the first index of that stress will be 3, right? So the first index of this stress will be 3. And the second index represents the direction. So in which direction is this stress acting? In the x1 direction. So this stress will be called tau 31, right? Tau 31. Another example, what's this stress called? This stress is acting on the right surface, right? The right surface is perpendicular to the x1 direction. So the first index will be 1. Also, it's acting in the x3 direction. So this stress will be called tau 13. Very simple. So what will this stress be called? This stress is acting on the left surface, right? Again, its normal will be the x1 direction. So the first index will be 1. Second index, the direction is also in the x1 direction, right? So this stress is actually this one. I'll call it P11. So I guess now you have learned how to name the stresses, right? So why did I call this stress and this stress to be tau, but this stress to be P? Well, do you see the essence of the two kind of different stresses? What are the taus? They are shear stresses, right? They are shear stresses. But what are the P? But what is the P11 here? It's a normal stress. So the normal stress, I'll call it to be P. because the normal stress, if I attach a minus sign behind it, it will be the pressure, right? So that's why I'll call it to be minus P11, minus P22, and minus P33. But all the other stresses, here and here, they are all shear stresses, so I'll call them to be tau. Okay, so there's a way for us to decompose the stress tensor sigma, which is something like this: minus P times the identity tensor, and plus this thing, the tau. I said the I here is the identity tensor, right? It has an effect to make a scalar into a second order tensor. Basically, it does that. So the I, if written out, is something like this. It's just like an identity matrix, right? So what is the P? The P here isn't the same thing as the P11, P22, or P33. The P here is what we call the hydrostatic pressure. So we know that in this case, the fluid may be moving, right? But we extract the hydrostatic case from it, and we are left with the effect from the movement, right? So this part is like how we deviated from the hydrostatic case. So this part we'll call it to be the deviatoric stress tensor. Okay, so if written explicitly, the tau will be sigma minus this thing, right? So it will be P minus P11, P minus P22, P minus P33, tau 12, tau 13, tau 21, tau 23, tau 31, tau 32, and this deviatoric stress tensor is the result from the movement of the fluids.